So we finish up weak acid, weak base problems with equilibrium problems. We're about to head into full titration calculation problems, which has us calculate at various stages of a titration, which you guys watch a pre-lecture on. Let's do a quick review on the final type of equilibrium problem for a weak base, which is actually your dream problem. You're kind of given all the information that you need and all you do is solve. There's like no algebra at all involved, just number calculations. And then we'll talk about titration and we'll do a little demo of how titration works. And then we'll get into strong acid, strong base titration calculations. So for this one, first of all, could someone just give me their answer? What do they get? 0.01968 for KB. Excellent. That's totally correct. So the way that you would have gotten this is you would have had to go from the given pH to solve POH. So 14 minus the given pH, which is going to equal 1.10. And if you're given the pH of a solution and they don't say the keywords initial or before mixing, you know it's equilibrium pH. You know it's after the thorough mixing, okay? So then when you get the POH, you can go from POH to hydroxide concentration at equilibrium, which is going to equal 0.0791 molarity. So then what you can do is you set up your ice table. Okay. I'm just going to do meth again because I'm just too short. I have deprotonated meth reacts with liquid water and a hydrolysis reaction, because we're not looking at acid and base at the same time right now, really. We're really just looking at the base behavior relative to water, which is like the standard for like amphiprotic setting, okay? To protonated meth and hydroxide. So you do your ice table. And of course, you don't include water because that's a liquid or a solid, and we don't do that with H expressions or K expressions. And then, okay, you fill it in with what you know. So you know, originally you have a 0.4 solution of methylamine. You have initially no ions produced or protonation transfer. And then you know at equilibrium, you have a 0.0791. Stoichiometrically speaking, if we're looking at a monoprotic transfer, a one hydrogen transfer, you're going to change by 0.0791 for everybody. That's the change. And then the plus or minus just is according to what position your species is serving. Is 94? It could be the calculator. Don't really care. Close enough. 0.791. Okay. And then what you would get for math is you would get 0.3205 if you use my non-0.41. And you would get 0.0791, Maggie. And then you would plug into the KB. Okay. And you would get 0.019. And then to technically be to the right sig figs, you'd want to get 3. Ooh, you'd actually be reporting in 2 sig figs because of this pH. This given measured pH is a 2 sig fig. So this would become, based off of the calculation given above, 0.020 would be the KB here. No units. All right. And that's how you would do that problem. Again, these problems, the biggest thing you want to recognize is when you have an equilibrium problem, you kind of are working with 1 out of 3 types. They just go on repeat, okay? And then you just adjust for the given context, acid, base, or general K problem that isn't limited to an acid or a base. So, do we have any questions? Yeah.
What is the percent ionization?
Could you apply this to the percent ionization? Could you apply percent ionization? So remember for percent ionization, you have to be 1,000, your initial concentration has to be 1,000 times greater than your KB or your K. So what we see here is our initial concentration is 0.400 and our KB is 0.020. So 5% does not apply.
Well, we also couldn't have known that because we didn't know the KB to start.
Yeah, but you couldn't have known it. But I think what they're asking you is compare it to the problem above. Could you have used 5%? No. Yeah. Oh, well, that's even easier. Okay. What you can do to calculate the percent ionization is I have produced 0.0791 molarity of ions for particularly the OH minus ion. And I started off with 0.400 base. So what's my percent? 19.8% ionization in regards to the production of OH minus, which again is yep, perfect. Thank you.
Is that 19.8 figure related to 0.01968?
Oh, no, I think that's just purely lucky.
Wow.
Yep. So, excellent. Thank you. Thank you for helping me complete the problem. All right. So then, now we're moving into not so much isolated titration concentration in terms of, oh, I just have this one moment of concentration. Now we're looking at throughout an entire process of titration, the entire laboratory process of reaching neutralization point, when my moles of acid stoichiometrically equal my moles of base, how could I determine the concentrations of each species present? So that's what we're heading into. So you guys watched a pre-lecture on titrations. It's pretty self-explanatory in a lot of ways. Like nothing's super mind-blowing. And you even got a little pretty picture, which by the way was good enough for Maggie to recognize. That's how good it was. Okay. Hold your applause. Jeez, folks. So the really important part is always this indicator concept. Because like titration setup is like kind of like you can only pour so many things into so many places. Like you can only make this work so many different ways. Okay. But the trick is this indicator concept. And because it's going to become a huge topic as we look at titrations for a weak base or a weak acid. But our whole ability to accurately pinpoint and measure the amount of titrant used, which tells us, therefore, or reveals to us the amount of analyte present, is that we choose an indicator whose endpoint, whose color change matches or aligns with the same region of pH where your actual acid and base are neutralized. Because if you have the color change when there's still way more acid than there is base, you're telling me a false signal. So what we got to do is we're choosing our signal, basically. We're making sure our signal is timed correctly according to pH. That's what an indicator is. It's a correctly timed signal that I've reached neutralization. Okay. So there's a lot of like terminology and conceptual nature behind indicators that they're really actually their own weak acid interaction. Like they're a reaction within a reaction. We use this little reaction to determine and indicate the bigger reaction, the one that we actually care about, but it's technically having its own chemistry without affecting the actual chemistry of the species that we care about. It's a side adjacent parallel chemistry, okay? The biggest thing here, though, that you need to realize is, one, I pointed out a very important part of indicators that reveals something about weak acid behavior and weak base behavior is that there is a point at what we call halfway equivalence when half of your moles, stoichiometrically speaking, are neutralized, half of the moles of your analyte are neutralized, that you can actually create an assumption where your pH measured in lab is your pKa. And if you can say that your pH is your pKa, you can do the math to find your Ka. And that's just a really quantitatively convenient thing. Okay. But that being said, other than knowing that it goes across two ranges, what you really care about is that you pick an indicator whose range of pH plus or minus 1 or pKa plus or minus 1 is across to where your neutralization point falls in the middle of that about. So Universal indicators, like we use universal indicators, are just a combo of a variety of indicators that change at different sects of the pH scale. So that they combo, so they cover the whole scheme. And then they have, of course, unique colors. So if you change to pink, you don't have to say, oh, is it the pH region of the scale at low end or the high end? Like it's all unique colors. Okay. And so what you guys were asked to do was quickly for the sample problem, given the following, okay, determine the range of, given the information above, samples of solutions were tested with 3 different indicators. Determine the pH range of the solution given the results shown below. So what you had to do is you had to recognize that based on this color change, okay, for the indicator, when we put in the indicator in one sample, it was thymolphthalein was colorless. So what you would have had to recognize that this is revealing a pH of less than or equal to 9.4. Okay. And I think, did I actually go through this in, did I actually go through this in my AP problem?
No,
you told us to.
Oh, how interesting.
So go do it. Come to class with this.
Go do it.
Yo, okay, interesting. For some reason, I thought I videoed this actually. Okay, so this one, how weird that it's not, what's this?
Yeah, thymolphthalein is just like not there.
Oh, well, you could have Googled it. Okay, and then for bromethyl blue, a blue color indicates that you're in a pH range of greater than, it's blue there too, so I said 7.5. A pH of greater than or equal to 7.5. This is all the same sample, by the way. This is like looking at three takes of the same sample, same solution. Then a yellow color of thymol blue, when I added thymol blue into another sample of it, I get yellow. So that tells me that for thymol blue to be yellow, it is in a pH range of less than 8. And like greater than 2. So we could do that. Less than 8, greater than 2. So then for us, what we want to do is we want to choose an indicator whose pH range falls within the equivalence point, plus or minus 1. Okay. So this is a little weird, but what we're seeing here is that most likely we're not seeing this is kind of an outlier range. It just looks like an outlier at this point. But what we do see is a color change between blue and yellow. Okay. Between the tight range of between 8 and 7.5. Okay. So based off of this, you would probably guess that your equivalence is occurring at a range of around 7.5 to 8. So whatever you choose, whether it be, I would probably pick bromethyl blue, or I'd probably just pick bromethyl blue. I think that's the only one that hits that range where you see a transformation occurring within that. Okay, that would be very clear. You wouldn't have to worry about it being a misconstrued analysis. Okay. So that sample problem, I think, is actually harder than most of the actual indicator problems on the AP MCQ. They tend to be like painfully obvious.
It's a little strange because they don't actually quite overlap.
I know. It's weird. It was a weird example problem, but that's what the textbook gave. So I was like, well, let's go with it. Okay. Do you get the idea though, that you want to pick an indicator who signals at the right time? It's kind of like the idea of like whoever sets up all of the like street lights, you hope that when you're the pedestrian walking go, that the other direction is on red. You want it to be timed right, so it aligns.
Wait, why is it 9.4 and not the 7.1?
It's not the 9.41. I was saying this was an outlier.
Because specifically, bromethyl blue turns green pH of 7.
So it just didn't, that sample kind of revealed that that probably doesn't have any effect. You're in a range outside of the equivalence. You've either passed equivalence or you're before equivalence, depending on which direction your sample is running. So now we're getting into standard types of titration calculations. I'm going to pretty much breeze past this because a lot of this is old solution molarity calculations just within the context of titration. Because I really want to get us to strong acid, strong base titration calculations where we actually track the curve. So if I were you, I might actually recommend you guys just listen to this part, okay? And maybe write down a couple notes, but I would just recommend listening. So for this problem, and here we're going to assume strong to strong. Here we're assuming a strong acid, strong base as our kind of the precedent for which we complete these calculations under. So here's the idea is that I could ask you at any point, and by I mean the AP, to find the solution of a concentration in a given titration situation. So here I have 25 milliliters of H2SO4 and 46.23 milliliters of a standardized known solution of 0.203 molarity NaOH. And I reach equivalence. Calculate the original strength of the acid. So all you got to do is one, set up your chemical equation so you know stoichiometrically what you have to meet. So you're going to get 2 NaOH for every 1 H2SO4 strong acid goes to completion to make sodium sulfate and 2 water molecules. Okay. And don't forget with a strong acid, strong base, you always form an ionic compound in water. It's kind of like one of the signatures for identifying if you're strong acid, strong base. Okay. Let's say you don't remember all the strong acids or strong bases, but you get a very distinctive ionic compound in water molecule. You're working with a strong acid, strong base combination. Then what we say is, okay, well, I know that stoichiometrically speaking, that the moles of my titrant, my known, have to equal the moles of my acid analyte to reach equivalence. So the moles of my titrant is going to equal 0.23 moles per liter times the liquid amount that I used, and that was 46.23 milliliters. I'm going to turn that into liters, so 0.04623, and that gives me a molarity amount of 9.385 times 10 to the negative third moles. Well, that means that stoichiometrically speaking, okay, my moles of acid then have to be compared. So comparatively for my moles of acid, it's going to equal 9.385 times 10 to the negative third. But according to stoichiometry, it's 1 acid for every 2 base. All right. So I get a value of the moles of acid present in my original sulfuric acid that's being neutralized at equivalence is 4.692 times 10 to the negative third. And then all I got to do is, now that I know the moles of my acid that were neutralized, I just got to figure out molarity by dividing by the volume I had. So, wow, my stomach is like going cray-cray. So my molarity of my original acid is 4.692 times 10 to the negative third, all over 25 milliliters, which is 0.025 liters. Guys, my stomach is going crazy over here. Oh my goodness.
All that Sriracha. Take that flask of
Yeah, perfect. Perfect. Just swig. Satisfied. Okay, 0.188 molarity would be my answer.
Even better, like sodium hydroxide.
Yeah,
Great.
perfect.
Yeah.
So let's quickly take a look at what titration looks like. Okay, this is a titration. I chose a weak acid just so I didn't have to use, yeah, this one was available to me. But let's look at what titration would look like to reach equivalence. How would I know I reach equivalence in lab? This is how I mathematically know. This is how I mathematically confirm it. But let's see what it looks like in lab. It's a really fun process, folks. So what we have is we have a Biret, a Biret pipette. And by the way, the Biret counts down. So notice, it goes from 0 up top down to 50, or 25 is our common. The reason why is that we need to track, we need to track how much liquid we're using and it goes down. So it's easier instead of doing math 50 minus this, it just counts as how much you're using as you're using it. And then what we have is an analyte solution. And that has a universal indicator in there already or phenolphthalein indicator. Okay. We tend to use the pink. So let me put up a white piece of paper behind it.
We also know the volume.
Well, that's hard to see. Yes. So if you look on the board, our standard solution, we're using 0.1 molarity sodium hydroxide that we're going to titrate into it. So we call it a titrant. And then we are have an analyte amount of 50 milliliters, and we're trying to figure out its concentration. So watch on the screen. I got to use the white to show it off. Hold on. Oh, maybe. So as I titrate, it turns and flashes of pink. Maybe the paper underneath would be good enough. Okay, as I titrate, it turns to flashes of pink. Now, automatically, it turns to flashes of pink for this reason. You're dropping in a very narrow amount in a very small location of your analyte. You're dropping in strong acid. So of course it's going to reveal a strong pH change initially because it's a small amount of space that it's interacting with. But as you swirl it, you start noticing that it's interacting with all the molecules, it's colliding. Then you'll notice that, oh, I still have excess acid left in there. That's why, so I had someone ask me, I was like, well, doesn't it mean it's already neutralized once it hits that pink flash? I'm like, no, man, it means you just didn't let it spread enough. Stir the darn thing, okay? So I'm going to keep going. And this is where it gets super finicky. So here's the problem. When you overshoot, that's bad because then you overestimate the amount of acid, the molarity. So your goal is to never overshoot, but it's also to never undershoot. So it's actually to be perfect. Yes.
Perfect is like drops in the half.
Yep. It's usually a half drop that gets you. Because it should turn to be, you want the color change to be lasting, but at the most barely detectable level of you barely change color. You're just like there. You just see this fade, like the blushy pink, like a super little cute blushy peach pink. Okay. See that level of pink there? That means you overshot. If your whole thing turns, and by the way, it takes one drop to do that.
Great.
So that's what you have to look forward to post AP exam. We do about a lot of these. But you get better each time, except that as the time goes on, I don't tell you what's the safe amount. So you have to start as if you don't know the whole time.
You just have to redo it as
And yeah, if you mess it up, you have to redo it. And you have to get like 3 trials. What am I at? Oh, I've used 8 milliliters.
Are you doing exactly one drop?
No, I'm sending it.
You're doing way too much.
Yeah.
I'm waiting for the whole thing to turn pink. See, the longer the pink lasts, the closer I am to getting. So it's lasting kind of long. I'm getting close then. Set it on a drop at a time.
That stirs automatically.
It's not going away.
Hold on, hold on. If you stir these sometimes for 5 to 10 minutes, it does go away eventually.
Oh, but that's great. So I may have to stir my little freaking beaker for 5 goddamn minutes.
Our solution is not.
We're getting close.
Safe estimate is very safe.
Your safe estimate was super safe.
Yeah. Yeah. Plus, think about how much time you have to at least plus or minus 5%.
It's like Russian roulette with this stuff. It's like, will you hit the equivalence point?
Have you not seen that movie? Funniest movie. The Lego Batman.
What's the tolerance for this? Like plus or minus.
Oh, guys, we're getting.
One drop.
One drop.
It's actually a half drop, but it's really hard to slice the bubble.
Yeah, why don't you just get
Don't mind me on this. No, I can make another paper every time I ever flip.
Yeah, that would work. What's the standard for one drop? Is it like a 10th mil?
I think it's, I don't know, actually. That's a great question. It depends on the pipette. Things to look forward to. Oh. I literally have no idea how much this is going to take.
You just like dump it.
Yeah, pour the whole thing in so you can see what
That's
it's
what I
like.
said. See what overshooting looks like.
Yeah. So we
I want to show you what equiv looks like, though. Oh. Oh, it's so good.
How many mils have you used?
I can just picture like imagine like the sound in this room.
Oh, hold on, hold on. Hold on, hold on. We might have done it. Hold on, let me stir it. I think I overshot it by a half a drop. It's too pink. It has to be the soup. Oh, it's stirring away though. Hold on. It's stirring away.
Oh my god, it's gonna go away.
Is it gonna go away to clear? Got it. Who's amazing? Your chem teacher. Look at that. That's the faint pink that we want. That is the time. Oh, did it already go away?
I think it went away. No, it definitely went away.
We were really close. Huh? What I do is I control the drop size. So I make it a super small bubble and then I knock it.
I didn't go in.
Hold on.
She's trying to get it connected to the bubble.
Guys, I think it is a pink.
There's a little pink.
It's a little.
It's a little pink.
I'll get a half bubble. I'll get a half bubble size.
Well, it looks bigger if you look at it like in real time.
There it is. There's my half bubble.
Lift it up.
Smack it harder. How is that? No. You're gonna accidentally like dump it.
Ha ha ha. Oh, it's still kind of clear. All right.
He's still clear.
Okay,
It's-
just overshoot it. All right. Just overshoot
Just yeah, okay, we know what we're looking for. Just overshoot it.
Hold on.
Oh, yeah.
Oh, no.
Hold on.
Oh, no.
Hold on. Hold on, folks. I might have overshot with that extra drop, but it looks like it's going kind of paler. So we could stir it for 10 minutes.
I love you. Don't think. I don't know that that's what we're looking for.
So this is too dark. It should have only said one drop. I did a drop and a half because I didn't control it enough.
A drop and a half. How dare you?
I know. Well, what it is it's now an overestimate of the acid present. But what we're looking for,
Okay, let's put more in.
if you had more water, you just diluted it. What are you doing?
Yeah, you could put more acid.
Can we add more base?
Okay.
Subtract.
So this technically would be passable for equiv, but I would want it even lighter. Okay. Now, if we overshoot, this is what happens. Yep.
I think
Too
you
late.
lied.
So that's what overshoot looks like.
You are supposed to measure.
So what we would have done is at equiv, we would have figured out how much titrant we used. And depending on the amount of titrant, that would have been what we called the amount. So like, for example, in the problem, we said we used 46.23 milliliters of that standard solution. That means I used almost the entire beret to neutralize. That would be what this problem would be saying, is I used almost the entire 50 milliliter beret to get to very, very, very faint pink. It's pretty. This used to be my horseback riding color. We have themes.
Oh, no.
Uh-huh. And I was a bright orange neon, a fuchsia, a green turquoise, and I was also black for my theme colors, and you have to custom outfits for each one that theme.
Like, we'll either play sports
So.
in like black, white, or red,
So.
or in like
All right.
neon green and yellow.
I don't really feel the need to go through this because honestly, do on your own. Like, because I really don't, yes. I really don't think that this is something that you should feel that you don't know anymore. This is basic math from like unit 3. Okay. So how about, what if I asked you to find the required solution volume? Okay. The required solution volume. This is again a review. I would recommend you just listen instead of write, unless you really cannot handle not writing. Okay. This one is, here I have, what was the volume used given a solution that's been mixed with a pH of 13.5 at neutralization point, so at equivalence. Okay. And what we get is, we are going to write out the balanced chemical equation so that we know stoichiometrically speaking what we're working with neutralization. And again, you're noticing this is a strong acid, strong base example because we create a solid and a salt ionic compound. We know that based off the problem information, we've used up for the moles of acid, where acid is our titrant. Now we're analyzing a base, an unknown base solution. We say that it is 0.423 molarity times 0.025 liters, because that's the amount that we use, that we titrated in. And that gives us a value of 1.058 times 10 to the negative 2 moles of acid. So then we know that stoichiometrically speaking, the moles of base are going to be 1.58 times, 1.058 times 10 to the negative 2. Okay. Stoichiometrically, that would mean that I am neutralizing 1 strontium hydroxide for every 2 acids. Guys. So I got to keep moving or else we'll not finish. That gives us a value of the moles of base being neutralized as 5.290. So at equivalence point times 10 to the negative 3 moles. So what that tells me is I need to figure out the volume, which means I need to figure out the original molarity. So what I'm told is that my standard, I actually misread this. My standard base solution has a pH of 13.50. If I know the pH, I can say that I can figure out the pOH of my base solution, which is going to be equal to 14 minus pH, which is going to be equal to 14 minus 13.500, which is then equal to 0.500. Okay. And that is the pH, well, that's the pOH of my original solution that I'm trying to find the volume of that I used, okay, or that I have present in my analyte. So then what I say is, okay, well, if I can figure out the pOH, I can figure out the amount of base present, okay, my molarity of my base. So I have strontium hydroxide, okay, for every 1 strontium hydroxide, I produce 2 hydroxides. Okay, so that means that the molarity of my strontium hydroxide is going to equal the molarity of my OH minus determined from taking the 10 to the negative pOH, divided by 2. Because what I'm saying is that potential of hydroxide, that pOH value, is the result of 1 strontium hydroxide molecule producing 2 hydroxide ions. So what we then get is that, okay. I see. What we then get is a value of 0.1581 molarity. And that gives me the value of the actual base source. Now, if I know that molarity of my actual base source, and I know the moles that were neutralized, I can figure out the amount of liters. Because I can say that 0.1581 moles per liter of my base is equal to my moles determined above, 5.290 times 10 to the negative 3, all over liters. And what I do then is I solve for X liters, and my X value, okay, my X liter value, oops, is X equals 33.4 milliliters was in my solution of base. That's how much volume I was analyzing of my base analytes by using my known titrant of acid. Okay. So we're going to skip that practice problem because we just don't really have the time to go through it. But you guys can do it tonight for homework. You should know that the answer for this is going to be 38.6 milliliters. And if you do the problem above, I should mention that the answer for this one, for the problem above, is going to be 6.03 times 10 to the negative 2 molarity. Okay, but don't worry, you can also look at this on my website when I upload the finished notes. So that's your first two types of strong acid, strong base titration calculations they could ask you as part of an FRQ. It's just like part of one, okay? And then we're going to apply it within the curve of the titration process. But we could also ask you to find molar mass, okay? Molar mass is really easy. So here's why. You do the same process of, for this problem, we have NaOH reacting with some monoprotic acid to produce Na, the acid, and H2O, okay? What we get here is we would be told that we have this amount of known titrant, 28.10 milliliters of a basic standardized solution. Oh, the basic standardized solution that is a 0.1261 molarity. What we know then is that the moles of my base, all right, the moles of base, my NaOH, is going to equal 0.1261 moles per liter, because that's the known molarity, times however much I used to reach equivalence, which was 0.02810 liters, giving me a mole value of 3.543 times 10 to the negative 3. Ooh, that looks way too crowded. Hold on. Equal to 3.543 times 10 to the negative 3 moles of base. Stoichiometrically speaking, because this is a monoprotic reaction, a monoprotic transfer of 1-to-1, that means that my moles of base are actually going to be equal to my moles of acid because it's monoprotic transfer. It's a 1-to-1 ratio. And so what I get then is that my moles of acid are 3.543 times 10 to the negative 3. And if I'm being asked, what are my grams or my molar mass? Okay. Well, I know that I was told in the problem that I have 0.328 gram sample of acid. So what I can do is I can take this value, and I know that molar mass is equal to grams per mole. So I can say for my problem, I have a sample of 0.328 grams. And I know that in that sample of 0.328 grams, I have this amount of moles, 3.543 times 10 to the negative 3 moles. I just divide and it gets me a value of 92.6 grams per mole as my molar mass of the acid, which I could then use to identify, relatively speaking, or tack on compositional analysis and do percent, okay, to figure out the empirical formula and then figure out the molecular formula. We could tack it on. Okay, but that's a pretty basic problem in terms of it's everything that you already know to be true. So you could do this on your own. And the answer is going to be for the next problem below. It's going to be a molar mass of 80.5 grams per milliliters if you were to try this out on your own. And this one does involve some stoichiometric non-1-to-1 ratios. It's a 1-to-2. So you're going to want to account for that.
I have a question.
Yes.
So, how do we know about acids, right? Is it a bad thing to have like a jar of 100% solid nitric acid in like perhaps like a bedroom closet?
Probably. You're supposed to be in a very much sealed case. like a cabinet.
So like you need that
It's-
to have it in just like your closet.
Yeah, it's highly corrosive too, and I believe it's pretty reactive
Oh,
and toxic.
yeah, I'll keep that in mind.
Okay.
So if I were to accidentally knock it over.
So if Sam were to break in and create an interesting chemistry experiment, okay, percent purity. We could do this and then ask you how pure is the acid? Because what if I give you a solution that's an impure acid solution? Only the pure part of that solution would be neutralized. The rest of it wouldn't. So you could then figure out percent purity of your solution. Ayo. Remember percent purity, okay, is, charging, is, you could do it by various things. We tend to do it by mass. So we tend to do grams of the pure all over grams of the impure sample, right? You could also do it via molarity of the pure versus molarity of the impure. All right. So for this one below, what we do is we have a reaction here between NaOH and NaHSO3. And it goes to Na2SO3 and water. Okay, again, we get a salt ionic compound and water. That's a really good indicator you're working with strong mix. Okay, that's like the number one way to figure out if you're working with a strong mix is that if you get an ionic salt and water, you don't even have to know that it was strong originally. Those products alone just tell you you're working with a strong. Okay. What you would get then is you would say that given the information above about the titrant, which here is our base titrant, we would say that to reach equiv, we know that we had to use 0.148 molar, 1.481 molar solution, and we had to use about 0.02026 liters of it, giving us a mole value of 0.00300 moles. And here we see this is clearly a monoprotic reaction, monoprotic transfer. So because we know that the moles of base is in a 1-to-1 ratio with the moles of acid, right? 1-to-1 ratio. We can say then that the moles of acid equals 0.00300 moles. All right. And I will quickly highlight this differently. Okay. And if that's the case, then we can say that we can take we know our acid is NaHSO3. We can multiply it by the molar mass of NaHSO3, which is going to be 104.1 grams of NaHSO3 per 1 mole NaHSO3. We get a pure amount then of pure acid to be a gram value of 0.3123 grams. And then what we do is simply, moving on to the next kind of stage, we divide this by our impure sample. So I'm turning this now into my percent purity problem of I had an original sample of 0.3470 grams impure. Times 100% gives me a percentage of 90.00% purity. So it's all math that you already know how to do, just based off of the equivalence perspective. Great. That's the first part. Let's now translate this to a titration curve. The whole entire process of figuring out as I'm dropping in titrant, what's the pH and what's the relative concentrations of each. So with titration curves, you're going to want to know how to draw them. That's just like a little tip. For AP problems, you want to know how to draw. So for a strong to strong, there's distinctive shapes for each type of curve. For a strong to strong, let's say where my analyte is acid and I'm titrating with a strong base, we get a curve that is distinctively looks like this. Pretty flat line, slightest angle, starting at a low pH because my analyte is acidic, to an increasingly slow, more basic, higher pH, to a sudden equivalence point shot up where I meet moles of acid, moles of base, to then overshooting, okay, into high pH range, excess strong base. That's the first one, where my titrant is strong base and my analyte is acid. You could also reverse the titration and say I'm starting with a basic analyte, and as I add titrant in drop by drop by drop, a slow decrease into a lower pH, more acidic, hits equivalence, bam, okay, at equivalence, and then overshooting more and more acidic as I keep on adding titrant. The big thing here to recognize is one is that your pH is always going to be 7 at neutralization for just a strong acid, strong base combo titration. This is not true when you are working with weak acids or weak bases. This is only true with strong to strong. If you were asked to write the net equation, what you would write is H3O plus and OH minus reacts to produce 2 waters. That would be an example of the net equation for this, because the sodium here is just a spectator ion. Okay. And this particular, this particular example would be demonstrated. It could go either way. Either one of these graphs, depending on what you decide, is the analyte.
Is it acceptable to write the ionic equation as H plus OH minus makes 1 H2O?
Yes, that would also be acceptable. You could write this as H plus. The only thing is it would be kind of weird balancing. So you'd have to like get a weird
H2O instead.
Yeah. It just, I think the reason that they like this better is that it balances out too. Okay. So, but it is technically, you're saying the same thing, but the AP would have you select this as the right multi-choice.
Okay.
Yeah. Okay. So I created a nice little graph for you, kind of marking the 4 stages for a strong acid, strong base titration calculations that we can do. So the first half of the graph is what we call the conceptual portion of this table. This is telling you what's actually happening in each stage of the titration curve. This is where the calculations, this is the actual math part. Okay. And maybe I'll just write math because that's shorter. So before equivalence, what we have here is we definitely have a pH way less than 7 because you're super acidic. Okay. And I'm just going to do because B/C, it's a strong acid. So that means to figure out the pH, which then reveals the amount of acid, right? Because pH is just a quick and easy way for us to signify, kind of signal the strength of acid or the presence of relative ions. But then, of course, we have the math behind the pH where we do 10 to the negative pH will give us our actual acid amount, right? So anyway, what we do here then is for titration problems, you're often just asked to go just to pH, and then they'll tack on if they want you to go all the way to molarity at the end. But for titration curve problems, when you're marking each step of the curve, they often just have you go to pH. So what would you do before equiv? Pretty much the amount of titrant that you add is negligible, right? Look at the slope. It's barely moving, okay? It's pretty much negligible because it's a drop at a time. So we just basically say, well, the pH is whatever excess hydrogen you have, right? Back to those excess ion problems, all right? Then there's halfway to equiv. You're halfway neutralized, which means that you have a gradual increase in pH as you become more basic. That's that really slight slope, okay? Your pH is still going to be less than 7 because you're still overwhelmingly, okay, acidic. And that's where you would get your excess problem, okay? And then you have equiv. Honestly, you don't even need to do the math. Usually you can just pretty much say it's 7 for a strong acid, strong base. You could prove it with your math, right? We've done it. You don't have to. It's just 7. Okay. And then finally, they almost never ask you to tell you for a strong acid, strong base. They probably wouldn't ask you what the pH is unless they want to give you a free point. Okay. Which they very rarely do. Okay. And then past equiv, your pH is going to be greater than 7 because you've overshot. Now you have excess OH minus base. Okay. So that means that your pH would be determined by figuring out your POH first. So what you'd have to do is you'd have to figure out POH of the excess and then subtract that from 14 to get the pH of your sample, which is going to be a very high pH. It's going to be in the ranges of 12 and above. Okay. So we have a new table that we're going to be introduced to called an ICF table, which represents initial change final, where F stands for final here. Okay. And it helps us represent the final concentration, i.e. identify the excess that we have left over between halfway and past that goes to completion. So notice this is not necessarily an equilibrium. This is not an equilibrium table. This is a how do I quickly find the excess? It's basically the math that you've done before, just put into a table format. Okay. So for this problem, okay, let's do a calculation. Gee willikers. At halfway to equivalence. I am not going to teach you how to do a calculation before equiv, because all you have to do is stick it into pH negative log. Like, I should not have to teach you that. So we're going to skip past that and assume that you are clear on how to plug into a calculator. And now we're going to go to pH second stage of the titration. Okay, halfway to equiv. So what we say here is we, first of all, need to recognize that we are going to deal with a lot of dilutions because now you're mixing two liquids. You've diluted your analyte sample. So what you have to do is you have to figure out the new concentrations first. So you would find that the concentration of diluted acid in this problem, where our acid is our analyte, okay? We know that at this point of our acid, we have 0.1 molarity times 25 milliliters over the total amount that's been added so far is 12.5 plus 25 over 37.5 milliliters, which gives us a value of 0.06 on repeat molarity, okay? Then we would find, and these are our diluted concentrations, then we'd have to find the diluted base concentration, okay? And we're told, okay, it's 0.1 molar also. And this time we've added 12.5 milliliters of the titrant. And to do our dilution factor, we divide it by the whole, 37.5 milliliters. And we get a value of 0.03 on repeat. So then what we say is now we set up our ICF table, okay? We got to figure out, okay, we're before equiv, which means we definitely have excess, okay? Definitely have excess acid. The question is how much do we have in excess? So what we say then is, according to our ICF table, our HCl reacts with our NaOH to produce NaCl and H2O. ICF, I initially, okay, don't care about the water. I initially have 0.06 because that's our initial diluted molarity. And I have initially 0.03. And of course, I have no salt yet, okay? And the idea is that I've used up, because if I'm at a half equivalence, that means all of my titrant has reacted. This is my, what we call limiting, right? It's our limiting. It's completely reacted with our acid titrant. So what we say is then we're going to use up all of our base, which means it's going to react in a 1-to-1 ratio for this example with all of our acid. We're following the stoichiometric process of change. And that means we've gained this much of the salt, molarity, okay, aqueous solution. So then what we get is we get that our final value at equilibrium, final value after completion of the titrant added is 0.03 on repeat, 0, because we just used it all up, right? And 0.03. And then what we say to ourselves, okay, so based on this amount of acid remaining, what's my pH? It's going to be negative log of 0.03. And that's going to give me a value of 1.477. And that's my pH after 12.5 milliliters of titrant have been added. Once I've reached marking halfway to equivalence, half of my moles of acid have been neutralized. That's the pH that my solution will show. Okay, that's the first problem. What about pH at equiv? Literally, don't even waste your time. Like you could figure this out. I wouldn't. I would just say pH equals 7. Like your math will show that your moles of acid are stoichiometrically perfect. Are stoichiometrically equal to your moles of base. You're just gonna get a pH of 7 in lab. That's what it's gonna show. Mathematically, it kind of gets weird, honestly, if you like carried out the full problem. It's just pH of 7. Strong acid, strong base. Don't even waste your time on the math. They won't ask you to anyway. The only time they would ask you to solve for equivalence is like in previous problems where it's pertinent for you to find some other part. But if they're just asking you to figure out the pH at equivalence for a strong acid, strong base, don't show any math. Just write 7. Save yourself some time. And I have not looked over here for like a hot 10 minutes. Okay, next one. Final problem. What about after equivalence? You overshot. You got that hot pink fuchsia. You are fighting for when's Breast Cancer Awareness Month? October. You are in the theme of Breast Cancer Awareness Month. You're going hot pink. Actually, I guess it's kind of a pale pink. But anyway, okay, how would you do this? You're going to do the same process that you did up here, except this time you're going to now have excess final of your base, okay? So what we see here is, I'm going to show you without the ICF table to show you just how you could also use the old method, okay? What you have here is you have some amount of sample. You need to first figure out, of course, your diluted amount, okay, your dilution. So we have HCl. This is the same. We're going through the same process. We're literally doing the example reaction that I showed you up here. We're working through it together right now. We're keeping the theme. So diluted, according to the information above, I do a dilution factor of 25/55 because that's the total new volume. I don't really feel like showing you how to dilute this again. You can calculate without me your dilution factor, but what you would get is a diluted amount of 0.05 molarity of HCl past equivalence at this point beyond equivalence. Then you would figure out your base. And you would also find that, ironically, you also have a dilution. Oh, I am looking at my wrong problem. Hold on. Sorry, guys. I looked at my wrong problem. 0.04545 molarity, given the information above for diluted acid, which, by the way, this would be completely neutralized at this point, by the way, right? Because you're past equivalence. And then 0.05454 molarity, okay, for your diluted concentration of titrant that you've added, which would be now an excess because you're past equivalence. Now you have way more base titrant than you do acid. Your acid has been thoroughly neutralized in the analyte. So what you would see here is you could set up an ICF table. You could totally do that and you would do this whole process, except now your limiting reactant is your acid. You just assume that you've used up all of your acid concentration. But what I would do is I would use your old school method of just figuring out the excess by doing subtraction, basic subtraction, okay? Because there's no question about it that there's anything else to consider. So you just do excess base, and here you can safely assume that NaOH is in a 1-to-1 ratio of OH minus production. So you can assume whatever the concentration of NaOH is the concentration of your hydroxide base ion present in solution. And you just do NaOH minus HCl. And what you would get then is 0.00909 molarity. And then you would just simply, to figure out the pH of it, because we really never report in pH. We just have to use pH if we're told things in the base perspective. What then we do is we say, well, pH is going to equal 14 minus POH. So I will take 14 minus the negative log of 0.00909, and I'll get a value for pH of 11.959 to 3 sig figs, 1, 2, 3, using the logarithmic sig fig calculation. And that makes complete sense. If I am titrating with a base, my pH past equivalent should totally be in the basic range of higher than 11. or at least higher than 7, but it's a strong base. So it's going to be a pretty intense pH. And that's how you would mark every point in a titration for a strong acid, strong base using previous knowledge that you know how to do with molarity. Okay. You're just putting it now in the context of each stage. Hey, Jesse. All right. So tomorrow, that's our calculations. Tomorrow, we're going to start getting into weak acid, weak base titrations. And they are far more complicated. They have 3 more stages outside of these 4 because there's this unique region in them. And we're going to learn about a new equation that we can use to avoid some of the extra hassle of calculations. But otherwise, guys, you have an AP problem tonight. And you also have a ton of practice problems that I didn't do in the workbook that you could be practicing here. Sorry, in the notes, as well as the workbook. So good job, you guys, and best of luck.